शाम बखैर और द ब्लैक होल में खुशामदीद। जिस तरह बाज़ औक़ात वाजबी किरदार रुख कहानी का मोड़ देता है, वैसे ही a butterfly flaps its wings in the Amazonian jungle and subsequently a storm ravages half of Europe. यानी small shifts can lead to massive alterations of the end result. मगर कैसे? यही आज हमारा मौजू है, यानी chaos theory. Chaos theory happens to be one of the three revolutions that physics underwent in the 20th century, alongside general relativity and quantum physics. In today's talk, we will learn about the fascinating history of how chaos was discovered, what distinguishes chaotic systems from non-chaotic systems, how scientists study chaotic systems, and the fascinating applications of chaos to fields as diverse as physics, astronomy, chemistry, बायोलॉजी एंड इकोनॉमिक्स। और इस दिलचस्प मौजू पर गुफ्तगू करने के लिए मेरे दाएं जानिब मौजूद है शहरयार ख़ान। ही इज़ अ ग्रेजुएट ऑफ फिज़िक्स फ्राम कायद आज़म यूनिवर्सिटी इस्लामाबाद। हिज रिसर्च इंटरेस्ट्स रेंज फ्राम कॉस्मोलॉजी टू कंडेंस्ड मैटर फिज़िक्स टू chaos थ्योरी। और इसके अलावा भी, क्योंकि शहरयार हैपन्स टू बी अ गुड फ्रेंड, अ गुड कुलीग, क्योंकि आप यहाँ द ब्लैक होल में साइंस लैब इंस्ट्रक्टर भी हैं, तो हम तो बहुत इंजॉय करते हैं इनके साथ डिस्कशन। उम्मीद है आप भी उतने ही महजूज होंगे। प्लीज़ अपने सेल फोन साइलेंट मोड पे कर दे सो दैट देयर इज़ नो डिस्ट्रैक्शन व्हेन द हाउस इज़ ओपन फॉर Q&A। प्लीज़ आप इसमें ज़रूर अपने फीडबैक और क्वेश्चंस के साथ शरीक होइएगा। बस एक चीज़ का ख्याल रखिएगा कि पहले अपना हाथ बुलंद कीजिएगा ताकि ये माइक्रोफोन आपको दे दिया जाए। इसके बगैर अगर आप बोलेंगे तो आपकी आवाज़ रिकॉर्डिंग में नहीं आएगी और ऑनलाइन ऑडियंस तक नहीं पहुँचेगी। एंड दैट्स इट। नाउ प्लीज़ वेलकम शहरयार ख़ान। थैंक यू।
Assalamu alaikum everyone. Welcome to the black hole. So I'm Shahriyar Khan, and today we're going to be talking about a very interesting topic, as you can see on the blackboard: chaos theory and the butterfly effect. So, have any of you ever heard of this topic before? Chaos theory, butterfly effect, in any way, shape, or form before? Very popular concept, and many movies and books have been written about this concept as well, starring in Hollywood and in other places as well, in which a very small change leads to a very dramatic outcome. But we will look at it scientifically from the mathematical and scientific lens, and we will also discuss various applications of this very interesting subject. So let's begin. Okay. So first of all, we'll discuss what is chaos theory. Then we'll go into the history of chaos theory, how it was developed. Then we will discuss what are the criteria for distinguishing chaos from non-chaos. Then we will look at various examples of chaotic systems, and finally we will go through some of the interesting applications of chaos theory. So what is chaos theory? So interestingly, even though it has been studied for a very long time, chaos still does not have a clear universal definition among the scientific community. There are many different definitions, and we will discuss some of them, but none of these definitions completely captures all of the chaotic systems that we study. So till now, scientists and mathematicians have not been able to come up with a universal definition, but still lots of progress has been made. We know a chaotic system when we see one, and this is the case in many different fields, especially when the fields are in their infancy, and or when fields are in their beginning stages. Things are not usually clearly defined in the beginning. People are trying to figure things out, and after a very long time and after lots of hard work do we arrive at a proper, precise definition of things, and we will see this perhaps in the coming decades. So what is a chaotic system? Usually it is a non-linear system with many degrees of freedom, and it exhibits sensitive dependence on initial conditions. So non-linear system basically means that the variables that are defining the system, either they are not linear, so either they are raised to some power or they have some sine or cos function attached to them. So anything that is not linear, if a variable is present in that form in our equations, then that is a non-linear equation. And usually our chaotic system has many degrees of freedom. So if you have only one or two variables, then it's in continuous systems it is not possible to have chaos. But when you have many variables, then it is very likely that you will see chaos. And that is why in very large systems, for example in the weather system, which has thousands of different variables, you see chaos universally. So we will see some definitions later. So is chaos is equal to randomness? Because the word chaos, the dictionary definition, if you open the dictionary, it usually means, I haven't seen the dictionary definition, but suppose we open the dictionary, it will probably have something like unpredictable or random or something like this. But chaos in the scientific sense does not mean randomness, because if it was actually random, we would not be able to study it. Anything that is truly random is unpredictable, so there is no point in studying it. But actually the chaos that we study in science and mathematics, the chaos I'm talking about, it's not the usual interpretation of chaos that we talk about. Especially in the news, you will see the word chaos being thrown around, that the society has become very chaotic and unruly and so on. But this is a different kind of chaos. In our case, chaos is completely deterministic. So even though we are using the word chaos, all of these chaotic systems that we will discuss, they are completely deterministic. Deterministic means that from a given initial condition, a unique outcome will result. If it was random, then if I started from the same initial condition, many different results would have been possible. But since it's deterministic, if you start with the same initial condition, you will get the same outcome. So it is deterministic in that sense. So why do we call it chaotic? Because it is very hard to predict. That is why we call it chaotic. We don't call it chaotic because it's unpredictable. It is predictable in principle, but it is very hard to predict. In practice, it is very hard. In principle, it is possible. So chaos is not equal to randomness. So as I told you, deterministic systems exhibit unique evolution. So there is no element of randomness in chaotic systems, even though we call them chaotic. The word that is used for systems that actually have randomness, they are called stochastic systems. Stochastic. So this is the technical word that we use for systems that actually have randomness built into them. So we use the word stochastic for them. But chaotic systems, they are deterministic. So that is an important point. So before chaos theory, all of the scientists and mathematicians and everyone believed that if a system is deterministic, then it must be predictable. And that is our common sense notion as well, that if I can write down equations for a system, then I must be able to predict it arbitrarily far into the future. But with the advent of chaos theory, that hope was shattered. And it was found that there are many systems, and actually the majority of systems in the physical world, that can be written in terms of equations and still be highly unpredictable, which is a very strange conclusion. And it is usually said that chaos theory is the study of, for example, if someone tells you somebody asks you what is zoology, and you say zoology, study of animals, and someone replies to you, a scientist replies to you, that zoology is the study of elephants, then that will be a very strange. You will say there are so many other kinds of animals, elephant is just one kind of animal. So when somebody asks you what is physics, for example, and you say physics is the study of linear systems, then that will be exactly the same as saying that zoology is the study of elephants. Because linear systems are a very small fraction of all of the systems that are possible. And most of the systems in the physical world are non-linear and highly unpredictable. So chaos theory is like the study of non-elephant animals, it is said in jest. Okay. So why should we study chaos theory, you may ask, if it is so hard to predict and it is deterministic but extremely hard to say anything about chaotic systems, because as I said, chaos is not pure randomness. So since chaos is not pure randomness, there must be some structure hidden within chaotic systems, and that is what we will uncover as we go through this talk. There are many interesting, if you probe deeply into chaotic systems, if you attack chaotic systems directly using equations, then you will not get very far, because solving the equations of chaotic systems is extremely difficult. But over the centuries, mathematicians and scientists found other ways to deal with chaotic systems and extract insights about them. And using those methods, we were able to uncover lots of different things about chaotic systems and learn a lot about the universe in which we live. So these are some pretty pictures of the Mandelbrot set, which you may have heard of, which is the most famous fractal discovered by the French mathematician Benoit Mandelbrot. So fractals, interestingly, have a very close connection with chaos, and I will discuss this later on. So these pictures are just to tell you that there is lots of interesting order hidden within the chaos. So let's go through some of the interesting history of chaos theory. So I guess as Niyar Bhai also mentioned in the introduction, that humans have probably had an intuitive notion of chaos from the very beginning, in terms of small changes leading to very big effects. So for example, Aristotle, thousands of years ago, he observed in one of his books on the heavens, he observed that the least initial deviation from the truth is multiplied later 1,000-fold. So he probably had some intuitive notion that sometimes small changes can multiply exponentially and lead to a very different result. There is a very old English parable from the 13th century. For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the message was lost. For want of a message, the battle was lost. For want of a battle, the kingdom was lost. And all for the want of a horseshoe nail. So this is a very old parable intended to explain that sometimes very small changes, very small, can lead to dramatically, because for example, if you study the origin of World War I and World War II, how were they started? They were sparked by a very small and apparently insignificant event, the killing of a particular person. And nobody would have guessed that the random killing of this person would lead to a global war and the deaths of hundreds of millions. So that is an intuitive notion of chaos, that small changes can lead to very big effects. So let's go into some of the scientific history of chaos theory. So as you people may know, James Clerk Maxwell was a very famous physicist who discovered the equations of electromagnetism. He wrote an essay, a philosophical essay in 1873 called Determinism and Free Will, in which he preempted the idea of chaos in some sense. So he said, and this is a very interesting article, but a small paragraph from this is, there are certain classes of phenomena, as I have said, in which a small error in the data only introduces a small error in the result. Such are, among others, the larger phenomena of the solar system and those in which the more elementary laws in dynamics contribute the greater part of the result. मतलब ये कह रहा है कि most of the systems जो जिनको हम study करते हैं, in these systems small error leads to a small change in the result. The course of events in these cases is stable. इनको हम stable systems कहते हैं. There are other classes of phenomena which are more complicated and in which cases of instability may occur. The number of such cases increasing in an exceedingly rapid manner as the number of variables increases. As I told you before, that chaotic system usually have many variables. So Maxwell had some idea of that chaos may emerge in physics and science. But Maxwell, in his essay, he was considering a large number of particles. Later on, the great physicist and mathematician Poincaré, he was the first person who actually discovered a mathematical system in which chaos was present. So Maxwell only gave a philosophical kind of philosophical reflections on chaos, but Poincaré was the first one who actually solved a set of equations and suddenly discovered that these were chaotic and these could not be predicted. And surprisingly, he discovered that you don't need a very large number of degrees of freedom or variables to see chaos. You can see chaos in as little as 3 variables. And actually there is a theorem called the Poincaré-Bendixson theorem, which says that if your system is 2-dimensional, then there can be no chaos. But if the system is more than 2-dimensional, like 3-dimensional, 4-dimensional, then chaos may be present. So chaos is not that far-fetched as people before thought. So even a system which only has 3 variables, if they are sufficiently non-linear, then they can lead to chaos. Only 3 and we will see a very famous example of this system as well, which only has 3 variables. So how did Poincaré discover the first chaotic system? So this is a very interesting history. We don't have a lot of time, otherwise I would have loved to go into it. But basically there was King Oscar II of Sweden, and there was a mathematician called Gösta Mittag-Leffler. So this mathematician Mittag-Leffler, he did a lot for the promotion of mathematics and education in his home country Sweden and in surrounding countries Finland, etc. So he had recently opened a new mathematics journal called the Acta Mathematica, which was one of the most famous journals in those times and still today. So to promote his new journal, he asked the king of Sweden, King Oscar, to please establish a prize, a challenge open to all mathematicians and physicists of the time to solve a certain problem. He actually gave 4 different problems. And whoever was able to solve one of those problems or more of those problems, his solution will be published in Acta Mathematica. So in one sense, he was using the influence of the king to promote his own journal and promote mathematics. So one of the problems in Mittag-Leffler's list was this. For a system of arbitrarily many mass points that attract each other according to Newton's law of gravity, assuming that no 2 points ever collide, find a series expansion of the coordinates of each point in known functions of time converging uniformly for any period of time. So they are basically asking you to solve the n-body problem, as it is called in physics. Have any of you watched the Netflix series 3-body problem, which was very famous recently on Netflix? So that also used this concept, chaos theory, to that was the main part of the plot. So this problem asked mathematician to solve the n-body, which is basically the problem that consider n bodies interacting gravitationally with each other. Can you predict their motion? So this is the problem. So Poincaré, it was announced in 1885. So Poincaré started working on this problem, and it took him about 3 years to do something about it. So 1888 he submitted his solution, but he soon found that his solution contained a major error. So his original solution, he discovered that for the 3-body problem, in which 3 masses are interacting gravitationally with each other, for example Earth, Sun and Moon, he discovered in his original solution that you can find a solution for it which could be predicted for arbitrarily large times. So he was very happy that I was able to solve the 3-body and give a formula for it. But later on he discovered an error in his proof. And after correcting that error, he discovered that no solution is possible for the 3-body problem. So you can, so no closed form solution, no analytical solution. You can't write down a formula for it. You can only approximate it. And you can just analyze it graphically. So that was a major discovery. So he submitted the revised version in 1890, and despite his solution being a little bit incomplete and despite his revision of the solution, he was still awarded the prize, the King Oscar Prize, and it had a gold medal and lots of a cash prize, a great cash prize. So Poincaré was the first one who discovered chaos in a physical system, and that too in just a simple 3-body system which only has 3 bodies. So imagine if the number of bodies was greater as it is in our solar system, which has many bodies, which has 8-9 planets, and every planet has multiple moons. So our solar system is extremely chaotic. But since the length scales in our solar system are vast, we won't see much deviation in the solar system during our lifetimes, because the solar system is such a vast system. But after 4 or 5 million years, it has been calculated that the solar system will also diverge from the present orbits, and some planets may even leave the solar system due to chaos. And before this, everybody believed that the solar system worked like clockwork, and it will always keep spinning and spinning like clockwork perfectly. This was a major blow to that deterministic idea. Even the solar system, if you fast forward time such that you pass million years in a minute, for example, then you will see the orbits diverge very rapidly and the solar system will become something else entirely. So this is a computer plot of the paths of the three body problem, and you can see that it is very, very complex and chaotic. It is not a simple motion. So Poincaré discovered this system, but even after this, people didn't take chaos theory very seriously. Because to study chaos theory seriously, you need serious computational power. You need to do lots and lots of calculations and make large graphs to figure out what's going on. Poincaré was a genius, so he was able to solve a system on his own without computers. But after Poincaré's work, people focused on things they could actually solve. So chaos theory fell by the wayside. But after the advent of computers and computational power, as computational power increased, people started studying systems, and naturally, somebody would predict a chaotic system very soon with the help of computers. So the first major discovery of this kind was made by a person called Edward Lorenz, who was a meteorologist at MIT. So he was innocently studying a simplified weather model on his large computer at the time at MIT. So this system was also very simple. It also had only three variables. This was the system on the right. This just three equations and coupled non-linear equations. So this also has a very interesting history, how he discovered the chaos. Just like the Poincaré story had a twist, this story also has an interesting twist. So he was in his office, and his huge computer in those times, computers were very, very large, the size of small rooms, and his computer occupied a large space in his office, and he used to work alongside the humming and buzzing computer, which produced a lot of noise. So he was inputting numbers and data into it and waiting for it to give an output. So one time he had to go somewhere, for example, I don't know where, cafeteria or something. So he had been simulating something on his computer, and before leaving, he started a new calculation on his computer. But what did he do? He used numbers from the middle of the previous calculation, and he inputted them, and then he left the room. And when he came back, the computer was still working and producing its graphs. And when he came back a few hours later, he was surprised to find that even though he had started with the same numbers as in the previous calculation, the new graph was significantly different from the previous graph, and he was shocked. First of all, he thought maybe my computer has backfired or something. Why is it giving such a strange? I inputted the exact same numbers as before. Then he started thinking. Then he realized that what he had actually done is that the initial conditions, the numbers he had used in the previous calculation, he had omitted their last three decimal places. So those numbers had 6 decimal places, very, very accurate. And he had inputted those same numbers but without the last 3 decimal places. So only a difference of thousandths and 100,000th part or millionth part in one. So who could have guessed that such a small difference in initial could lead to such a large difference in the outcome? So he realized that this must be chaos. This is not a technical error in the computer or something. That small change in the decimal places, the 4th, 5th and 6th decimal place only, after some time, it led to a completely different outcome. So he published this result in 1963. And the title of his paper was something like, "Does the flap of a butterfly's wings in Brazil cause a tornado in Texas?" So that's where the term butterfly effect comes from, because Edward Lorenz used that term in his paper. Previously, he was thinking of using some other animal's name, I don't remember which, but there are so many interesting historical accidents that happen when discoveries are be that you dig into the history, you find many interesting tidbits. So he had actually submitted this paper to a conference, and he had used some other term except a butterfly. He had submitted it, but the editor, the person who was supposed to publish it, he changed it to butterfly for some reason, because he thought maybe the butterfly is a better analogy, even though Edward Lorenz didn't. And so he gave the talk, and this became famous, and people started writing books about it, and even movies started being made called the butterfly effect. And it all started in this humble man's office in the 1960s. So after this, there was an explosion of work in chaos theory. People started finding chaotic systems everywhere, because once you start looking for something, it appears everywhere. So they started finding chaotic systems in simple population models and economic models and stock market data and everywhere. So this is a representation of Lorenz's equations in phase space, and this is another reason why it is called the butterfly effect, because when you plot the solutions of the equation of Lorenz, it looks like a butterfly. So that is also very interesting thing. So how can we study chaos? So these were just the historical trajectory of chaos. Now let's go into what chaos theory actually is, the meat of it, and how people actually study it. So as I told you in the beginning, there is still not a universally agreed upon definition of chaos. There are many different definitions. I will tell you some of the most popular ones and used ones. So first of all is the criteria given by Robert Devaney. He was a mathematician. He gave this criteria in 1989. So Robert Devaney said that for a system to be considered chaotic, first of all, it has to have sensitive dependence on initial conditions. So this means that, as I told you in the case of Lorenz, that if you start your system at a very tiny distance apart, a very small distance apart, 2 points which are very near to each other, after some time they will land on very different trajectories. So this is called sensitive dependence on initial conditions, abbreviated as SDIC. And in this image you can see, and this is phase space, and you start here in both of these plots, and these 2 points are extremely close to each other. They probably have a very small difference in the order of few decimal places. But if you follow their paths, initially they are very close, but after some time, a given fixed amount of time, this trajectory lands here and this trajectory is somewhere over here, and their shape is also very different. So after some time, they don't look like they started from the same place. They look completely different from each other. So this is sensitive dependence on initial conditions, and this is a hallmark of chaos. But this is not enough. You also need something called topological mixing. So for example, you can have something like this, a system like this, given by this equation. So even in this system, if you start 2 points which are very close to each other, and you apply this equation iteratively, after some time the 2 points will start to diverge, and as you move forward they will diverge more and more. So this is also sensitive dependence on initial conditions, but this is not a chaotic system, because I can predict where these points are going. I know that after a very large amount of time both of them go to infinity. So this is a very simple system. So we need something more, another criteria to distinguish chaotic systems from these kinds of systems. So that is something called topological mixing. And topological mixing basically means that in your phase space where your points are, if you take any small region of the phase space and you move forward in time, eventually that small region of the phase space will cover the whole phase space. So that means that the points are diverging so much even in a small region that after some time the points inside it will diverge so much they will cover the entire space. So they don't have a simple motion, and it is almost impossible to predict where a particular point will land. That is called topological mixing, that even a small region mixes with everything else. And a third criteria is density of periodic orbits, which basically means that there are many periodic orbits. Basically means that there are like the planetary orbits which continuously repeat on themselves. In chaotic systems, there are periodic orbits as well. They are more complicated. But they are density of periodic orbits means that there are extremely large amount of them, even in a small region. So almost anywhere you are in the phase space, you will find a point which leads to periodic orbit. So we don't have to understand this in much detail, but just for completeness, I am telling you that this is also found in almost every chaotic system. That there are lots and lots of periodic orbits. But this criteria has some flaws. For example, that it was later discovered that the criteria 2 and 3 they actually lead to criteria 1. So this means that criteria 1 is a little bit redundant. So people started coming up with others. So for example, another criteria of chaos is called the Smale's horseshoe. And this is basically given by a mathematician, a Fields medalist called Stephen Smale. And he basically said that if your chaotic system is such that when it evolves, it does something like this to the phase space. So for example, the Smale's horseshoe basically means that you start with the first figure over there, and this is the unit square. This one is a unit square. And then you squash it by 1/2, and then you extend it by twice, and then you turn it on itself. And then you repeat the process again. And when you keep doing it, you will form basically in this original square, you will form a fractal structure. And so Stephen Smale said that when you analyze chaotic systems, their phase space, they look like they have been put through the same process as this horseshoe. So this horseshoe is a good analogy, a good way to analyze chaotic systems in general. But still, this also has weaknesses because it does not cover every chaotic system. So this is the major problem right now, that there is no definition, clear definition that incorporates every chaotic system. There are outliers in every definition. So the last definition that I will tell you, this is the most mathematical and the most useful as well, called the Lyapunov exponents. And this is basically, I have given the equation here of the Lyapunov exponent just for completeness. So here you can see that there are 2 points which start very, very close to each other. But as time increases, they diverge from each other exponentially. And this is also a hallmark of chaotic systems, that points very, very close to each other, they diverge from each other exponentially. And this Lyapunov exponent, this basically tells you how fast this exponential divergence is. So the greater the value of this lambda, the faster the points, the trajectories will diverge from each other. So a system is chaotic if it has a positive Lyapunov exponent. If it has a negative, then trajectories will tend to converge onto fixed points or periodic orbits. But if it is positive, then trajectories will diverge. So this is a way of quantifying chaos. Important, very important. But this is also incomplete. There are some counter examples that exhibit chaos, but they have negative Lyapunov exponents. But still, this criteria is very useful for most chaotic systems. So this was the mathematical part. So now let's go on to some interesting examples of chaotic systems. So the first one, the most famous, as I told you, is the Lorenz attractor, also called the strange attractor, which looks like a butterfly, which was discovered by the meteorologist Edward Lorenz. This is one of the most famous examples of chaos, and this emerged from Lorenz's simple model of atmospheric convection. So let's try this interactive tool which shows you how it works. So this will show this. Okay. So this is the Lorenz attractor. You can move it around. It is a 3D object and you can see it from different angles. A very interesting pattern, shape. It's not working? ये क्या? ये क्लोज, मैं प्रेजेंटेशन तो क्लोज की हुई है. Wait a a second. ठीक है, अब नज़र आ रहा है. So this is the Lorenz attractor. So you can see it from different angles. This is the overall shape. It is a three-dimensional object. Okay. So now let's start a small with a small set of initial conditions and see how they evolve. So I will click on this small cube, and then a small set of initial conditions will start to evolve, and you will see that even though the starting conditions are very close to each other, eventually they will spread far apart. So these started from a very a small tiny box. They started very close to each other, but after a short time they are completely far apart and they look like they had nothing to do with each other. Can start it again. So that is how they started, but since the trajectories are so divergent, very soon they become completely different. So this is how chaotic systems work. Okay. Okay, so another famous example is called the logistic map, as is shown here. So this was basically used by biologists to study population dynamics of various animal populations and others. So this is only a one-dimensional map. So this is actually a discrete map. So this is not a continuous map. This is by equation. So this is a discrete map, and in discrete map means that you go in discrete time steps to the next point, as opposed to continuous. So in discrete maps, with only one variable, you can create chaos. You only need one variable. So this is one of the simplest possible examples of chaos. And you can actually program this yourself, this graph. And as you can see here in this graph, R over here in the x-axis, this is a parameter which basically tells you how fast the population is growing. And this x over here, this is the steady state value. After a very long time, what is the value of the population? So as you increase R, there comes a point when you enter this chaotic regime, where many different final states are possible. And when you keep zooming into this region, it will look like, at every scale it will look the same as before, as fractals do. So this region has self-similarity, and this is why this region is fractal-like. And this is an example of how fractals are related to chaos. Wherever there is chaos, you will find a fractal structure. Okay. Another example is this. This is called a Rossler attractor, just like we saw the Lorenz attractor before. So attractor basically means that when you start from any set of initial conditions for given parameter values, this is the kind of structure on which initial conditions tend to land after some time, after a very long time. So this is an example of how there is order hidden within the chaos. So chaos theory does not mean that if you start from a set of initial conditions, they will just fly everywhere and they will be completely scattered. If there was pure randomness, then this picture would have been like a TV static, for example, with no pattern at all. But you get this very definite pattern over here. So even though chaos is very hard to predict, if you zoom out enough and you see it from the right perspective, you will see the hidden structure inside chaotic systems, which have fractal structure usually. And some systems have turned out to have beautiful looking shapes as well. This one looks like a butterfly. So this is the order hidden within the chaos. This is another example. This is called a Rossler attractor, and this results from this set of equations. And this is even simpler. These equations are simpler than Lorenz's equation, and this leads to this kind of attractor. So even though this is a very complicated set of equations to solve, if you look at it in the phase space, this leads to a very interesting structure, a definite structure, not random at all. Very hard to predict, but certainly not random. And interestingly, this is used in chemistry to study the equilibriums of reactions, for example. When there are many chemicals interacting with each other at different rates, it becomes a chaotic system. It becomes hard to predict that after a certain time what will be the concentration of the different reactants. That can easily become a chaotic system, and this is used to model that kind of thing. Very useful in chemistry. So these are not just mathematical playthings, they have use in many different branches of science. Another example is double pendulum. So we made a double pendulum here as well, thanks to Alam. So as you can see, this is we just made this yesterday, so not that great, but still workable. So if you start from here, for example, very hard to predict. If you start from a very small amplitude, it will be easy to predict what it will do. It will act like a normal pendulum. But if you give it a very large amplitude, it becomes very hard to predict. Like this. Even start to spin. And if I start with almost the same, it led to a different outcome, even though I started at almost the same point. So that is what chaotic systems are like. Even though you started from very similar initial conditions, it will do something completely different. So now it did something completely different. It is very hard to predict this kind of thing. As you can see here as well, these two double pendula were started at almost the same position. But after some time, you will see that they will begin to behave very differently. Now they are starting to behave differently. And now they look nothing like each other. So a double pendulum is also a chaotic system because this has 4 degrees of freedom. And as I told you, when you go to 3 or more dimensions, chaos can occur. In a simple pendulum, it only has 2 degrees of freedom. So it is completely predictable. But as soon as you go one step further, double pendulum, you see chaos. This is another example. As you have seen, turbulence, fluids, when they have low viscosity, they mix with each other in a very chaotic pattern, as you see in weather patterns as well. And as you can see here, we have done this kind of experiment in our science lab as well for students, and we have made other kinds of chaotic pendulums as well, magnetic pendulum as well. So as you can see, it is very hard to predict where a certain quantity of liquid is going. Extremely chaotic. Okay, this is another famous example called the Duffing oscillator. It has this equation. So and in the phase space, the trajectories look like this, as shown on the right. So this is a damped and driven oscillator, and this is used to model certain phenomena in electrical circuits. So this was being studied before chaos theory became a popular subject. This was being studied in 1930s and 40s as well. But people noticed that it was very hard to predict the future of this kind of system. And this also became a very important example of chaotic system. And this cubic term over here, this is the thing that causes problems. If you didn't have this, then this equation can be solved completely. But as soon as you add this, there is a new degree of freedom in the system, and it becomes chaotic. So as soon as you give too much freedom to a system, it becomes chaotic, very hard to predict. Turbulence, as we saw. and fractals, as I told you earlier. So how are fractals related to chaos? As I told you before, even in the example of the logistic model, this over here, the green region over here, this is completely like a fractal. This is not completely filled. So this may appear to you to be filled, but this is not actually filled. This is lots and lots of holes in it. If you zoom in, you will keep finding spaces inside it. So this is neither a two-dimensional object nor a one-dimensional. This is a fractional dimension, and this is a fractal. And the more you zoom in, you will keep finding more and more empty regions and filled regions, and the pattern will keep repeating forever. So this is a completely bizarre kind of object. And these things as well, these are also fractals. So this is not a completely filled disk, even though it appears that way. If you zoom into it, you will find spaces and you will find filled regions, and it will exhibit a fractal like structure. Pattern will keep repeating. So this is neither empty nor it is completely filled. It is something in between. So since there is so much complexity in chaos, that is why you usually get fractals out of them. So this is one of the most famous fractals called Mandelbrot set. So this is plotted in the complex plane. So how do you plot this? So for any point if you want to see how it behaves, you use this equation basically, and if it diverges, and you color it with if it converges, you color it with black. If it doesn't converge, you color it with something else. So all of these regions in black, they are the ones for which this equation converges, and all the rest of the points do not converge. But this is not a simple pattern at all. It is simple in the middle, but on the edges it is extremely infinitely complex. And the more you zoom in, you will keep finding more and more and more structures, and people have simulated this to an incredible amount of detail, zooming in more and more and more, 100 times, 1000 times, and they keep finding more and more structure on its edges. It is like an infinite complexity inside it. You can never stop exploring it. This is a zoomed in image of a very small part of one of these branches over here, and you can see it is how complex it is. It has so many little structures inside it, and if you zoom into any one of these structures, you will find a whole new world again. As I showed you some examples of the Mandelbrot image before as well, now we will be able to appreciate it more. These are also zoomed in images of various parts of the Mandelbrot set on the edges. And this is zoomed in, this is further zoomed in, this is further zoomed in, and further zoomed in. And you can see that the complexity never ends. There is so much complexity. So how is this related to chaos? Because if you start, for example, if you are at a certain point and you move only a little bit to the side, you select a very, very slightly different point, then it may have a completely different color. That's why this has sensitive dependence on initial conditions, because there is so much complexity. If there was only a little bit of complexity, for example, then if you moved a little bit to the side, then you most probably would have had the same color that you started with. But since fractals have infinite complexity inside them, if you start at a certain point and you get yellow, for example, and you moved very, very slightly to the left or right, there is no guarantee you will still be at yellow. You might have brown or orange or something else. So that is why fractals are related to chaos. Small changes in initial conditions can lead to very different outcomes. And this is another very interesting thing which we also built in our science lab for students, and students actually built one themselves as well. This can be built by children as well using magnets. So you can build this. You can just have a hanging thread here, and you can hang a strong magnet from it, and on the base you can attach 3 magnets with opposite polarity to this magnet, so that when you release this magnet pendulum from somewhere, it will be attracted by all 3 of these magnets on the base. And if the amplitude is large enough, it will keep oscillating for some time, not randomly but chaotically between these 3 points, because this magnet is being attracted by all 3. And after some time, it will land either on yellow or red or green. And this pattern is also chaotic. So this is the pattern that you get out of this pendulum. So how are these regions colored? So if you start at any point, for example, you start here, you start here, where this pendulum is, and you release it. And after some time, you see that it landed on the red magnet. Then you will color this point red. If you started at this point, and after some time it landed on yellow, then you will color this point yellow. So that is how you get this interesting pattern. So who could have guessed that by doing this procedure you will get an infinitely complex figure? You might have guessed that I will probably get some a simple pattern, for example, a region full of red, a region full of yellow, region full of green. But close to each of these magnets, the regions are very simple, because if you start very close to this red magnet, you will almost certainly land here. So there is a large region which is totally red, and large region yellow, large. But as soon as you go in the boundary of those regions, in the middle of those regions, then there is great uncertainty, and even a tiny shift can land you either on red or blue or yellow. And this is what leads to fractal, because this is a chaotic system. This is called a magnetic pendulum, and this is the reflection of this. So chaos and fractals are intimately connected, as you can see. So as I said, there is always order hidden within the chaos. So as I told you, the Lorenz system leads to the strange attractor, looks like a butterfly. This is a very interesting example of order emerging from chaos. This is called a Galton board, and this was also made by our students in the science lab during the summer camp. So what is happening here is that you are releasing some small beads from the top, and these beads have many different choices of where to land, because there are many different paths over here. So predicting the path of an individual bead is extremely hard, extremely difficult, predicting where a certain bead will end up. But after this process has been done, it leads to a very definite ordered structure. This is a Gaussian distribution. So the points in the middle, most of the beads end up in the middle, and on the peripheries, there are not many beads. So this is another example that a system that seemingly looks very chaotic and unpredictable, if you look at it with the right lens, you can see the order hidden within it. Another example is weather versus climate. So it is extremely hard to predict the weather, as you all know. It is almost impossible to predict the weather 1 week into the future. As I told you about the solar system, that the solar system will become unpredictable after about 5 million years. So it is not infinitely predictable. But the weather has so many more variables that the time scale for that, this is also called the Lyapunov time of any system. This is the time after which the system becomes totally unpredictable. So the Lyapunov time for solar system is 5 million years, but the Lyapunov time for the weather is about 1 week. After 1 week, you can't say anything for sure about the weather, what will happen. But you can say something 1 or 2 days or 3 days into the future. But you can say a lot about the climate, because the climate averages out the little tiny perturbations in the weather, and it leads to definite patterns in the long term. So you can say a lot about the climate in even prehistoric eras and in the time of the dinosaurs, and even before that. Scientists have a good idea what the overall climate was like. But could scientists predict what the exact weather at a certain point where a dinosaur was, what was the weather over there? That is impossible. We can't even predict few days into the future. But we still know what the climate was like at that time, and we can predict with good accuracy what the climate will be 100 years from now or 1000 years from now, for example, based on current trends. Yes, उनका एक सवाल है. माइक सर ले लें.
No, I mean, you're right. In terms of the over long period of time, there was ice age and all those type of things went, so there were major shifts. But how can you say this with certainty that over a period of decades, like they say now, with given how the temperature is taken, you can take it from one street to another, and there may be some decimal point difference over a period of time. So is that not a chaotic system?
Yes, so exactly. So as I said, it is very hard to predict the weather in the short term because there are lots and lots of variables interacting with each other, and you have to take all of them into account. But in a long enough span of time, most of those little tiny perturbations, they tend to cancel each other out, and only some variables remain in the long term. So in the very, very long term, you can say something about the future of a system, because in the very, very long term, because in the short term, for example, if I want to predict what will be the weather tomorrow, there will be a million different factors affecting it. For example, the rate of emissions in the city currently, for example, the amount of forestation here, and many other factors, what the direction of the wind is. But over a long enough period of time, these small perturbations will tend to cancel each other out, and only the largest factors will remain. And then I can say something about the climate. So that is why. So as you can see in this figure over here, the weather is an extremely complex system. It has lots and lots of factors. Almost impossible to predict what will happen. But climate is orderly. That is why there is a whole science of climate change. If weather was unpredictable, then we wouldn't have been able to say anything about the climate changing. But every scientist agrees that the climate is changing very rapidly, and we need to do something about it. So more than 99% of climate scientists agree that the climate is changing very fast for the worse. So that is because climate can be modeled, but modeling the weather is extremely difficult. We can see the long-term trends in the climate. So let's discuss some applications of chaos. I have discussed some through the course of the talk, but let's go through many different fields. So first of all, as I told you, astronomy. As I told you, if you have more than three or more bodies, then in the gravitational system, then the system is chaotic. So there are many examples in our solar system and other places as well, in which there are for example, many asteroids or comets orbiting a certain moon, for example, or a certain planet. So predicting their motion is extremely difficult. But after the advent of chaos theory, scientists were able to use the methods of chaos theory to say something about those kinds of systems. And as I told you, we know something about the long-term evolution of the solar system as well. And this was actually done using large computations on like huge computers simulating the solar system for very large periods of time. And when they simulated the solar system, they found that it diverged very significantly from its current state after about 4 or 5 million years, contrary to what was thought before. So as I told you, physics. So it has lots and lots of applications in physics because most of the systems in physics are non-linear and chaotic. Only a very few इतने कि आप उंगलियों पे गिन सकते हैं इतने ये सिस्टम्स जो कि सॉल्वेबल हैं, एग्जैक्टली सॉल्वेबल हैं. बट मोस्ट ऑफ द सिस्टम्स आर नॉन लीनियर एंड chaotic. So it's like the study of non-elephant animals. You are talking about most of the animals. And there is a new branch opened up in physics called quantum chaos, which tries to relate quantum mechanics with chaos theory, and that is also a very interesting field. In biology, as I told you, when there are many species interacting with each other, for example, if you have only two species interacting with it, it is a simple system, you might be able to predict it long term into the future. But if there are many different species interacting with each other in a habitat, for example, and there are environmental factors as well and other factors as well, then it becomes a chaotic system. And then you can't give an accurate prediction, but you can use the methods of chaos theory to say something that what are the general trends. Chemistry, as I told you, the Rossler attractor, it is chaos theory can be used to study reaction dynamics as well, because most of the systems that you will study complicated enough will have chaos in them. You have to learn chaos theory to study these kinds of systems. Life is not that simple. Economic forecasting and predicting the rise and fall of stocks, for example, people have used chaos theory and fractals as well to predict these kinds of things because it's very unpredictable. Traffic modeling, sometimes traffic can become chaotic. As you know, in Pakistan it happens a lot. So we probably need a healthy dose of chaos theory to figure out what is happening in our cities, on the roads. And weather and climate modeling, obviously. So finally I will end with this. This is just a very interesting thing I found, not much to do with chaos theory, but still a good example of the complexity found in nature. So this is on the left, you can see a shell called a conus textile shell, and it has a very interesting pattern on it and seemingly appears random. But actually a guy called Stephen Wolfram, he discovered this diagram on the right, and this is called Rule 30. This is a cellular automaton, and this is a completely abstract computational system. And he discovered this interesting pattern which never repeats. It has an infinite complexity in it. And somehow nature has copied the almost exact same pattern on a shell for some reason, which is a huge mystery. I find it extremely mysterious. That what does this rule have to do with this shell? So this might be another interesting example of how chaos manifests itself in living systems as well. So there are applications to living systems and biology as well. Sometimes the heart can beat in a chaotic way and people can have heart attacks because of that. So people are using chaos theory on the echocardiograms as well of patients. Because if you don't know about chaos theory, then it will appear random to you how the heart is beating. If you have cardiac arrhythmia, for example, someone has. But if you know chaos theory, then you might be able to say something that it is not completely random, it is behaving chaotically, and how to save it, for example. So, okay, so that's all. Thank you. Any questions?
अस्सलामुअलैकुम। आइंस्टाइन ने जिस तरह कहा था कि गॉड डज नॉट प्ले डाइस, एक तो उसको इसके रिलेट कर दें और थ्योरी ऑफ रिलेटिविटी को एक्सप्लेन कर दें।
अच्छा, आइंस्टाइन ने जो कहा था ये तो क्वांटम मैकेनिक्स के उसमें कहा था उसने, इससे तो उसका इतना ताल्लुक़ नहीं है क्योंकि क्वांटम मैकेनिक्स के अंदर ना प्योर रैंडमनेस होती है एज़ फार एज़ वी नो। इसके अंदर तो बस सीमिंग रैंडमनेस है ना, इसके अंदर बस ये है कि कॉम्प्लेक्स इतना ज़्यादा है कि हम लोग उसको समझ नहीं सकते तो हमें रैंडम लगता है, लेकिन असल में chaos थ्योरी के अंदर रैंडमनेस नहीं है। अगर आपको इन्फिनेटली प्रिसाइज आपके पास डेटा है तो आप प्रेडिक्ट कर सकते हैं, लेकिन किसके पास है इन्फिनेटली प्रिसाइज डेटा? लेकिन तो आइंस्टाइन इससे तो ऑब्जेक्ट नहीं करेगा कि chaos थ्योरी क्यों है, वो कहेगा ठीक है डिटर्मिनिस्टिक है। लेकिन जो क्वांटम मैकेनिक्स है वो तो वाकई इनडिटर्मिनिस्टिक है, उसके अंदर वाकई रैंडमनेस है। तो फिर आइंस्टाइन को ये चीज़ बुरी लगती थी कि एक यूनिवर्स जो एक गॉड ने फॉर एग्जांपल बनाई है, जिसके अंदर हमें लगता है कि बहुत ज़्यादा ऑर्डर है और बड़ी ब्यूटी है उसके अंदर और बड़ी मैथमेटिकल लॉज पे चल रही है, उसके अंदर रैंडमनेस कहाँ से आ सकती है? नहीं आ सकती उसके अंदर रैंडमनेस। तो उसको बड़ी बुरी लगती थी ये चीज़। लेकिन क्वांटम मैकेनिक्स कहती है कि है रैंडमनेस, उसका कोई वो नहीं है, हल नहीं है इस चीज़ का। बड़े लोगों ने कोशिश की लेकिन वाकई में है रैंडमनेस। तो फिर इसलिए उसने कहा था कि ना गॉड डज़ नॉट प्ले डाइस विद द यूनिवर्स, के रैंडमनेस नहीं हो सकती यूनिवर्स में। और रिलेटिविटी तो डिफरेंट चीज़ है, इसका इससे इतना ताल्लुक। अब रिलेटिविटी के अंदर भी आप कर सकते हैं, जिस तरह मैंने प्लैनेट्स की बात की ना, तो बल्कि रिलेटिविटी के अंदर हैं इसके कुछ एप्लीकेशंस हैं। ब्लैक होल्स के अंदर भी chaos थ्योरी की एप्लीकेशंस हैं, वो काफ़ी फिर एडवांस्ड हो जाता है कि मतलब वो फॉर एग्ज़ाम्पल जो इंफॉर्मेशन स्टोर है फॉर एग्ज़ाम्पल इवेंट होराइज़न में, तो उसकी ब्लैक होल्स की मैं बात कर रहा हूँ, तो वो फिर उसकी जो क्या कहेंगे जो स्प्रेड है उस इंफॉर्मेशन का वो क्योटिकली होगा और बड़ी तेज़ी से होगा। इंफॉर्मेशन स्क्रैम्बलिंग कहते हैं उसे बेसिकली। तो कुछ लोगों ने ना एक पेपर भी एक लिखा था फिजिसिस्ट ने कुछ सालों पहले, उसका नाम था ब्लैक होल्स एंड द बटरफ्लाई इफेक्ट। तो लोगों ने ब्लैक होल्स पे भी chaos थ्योरी को अप्लाई की है। ब्लैक होल्स रिलेटिविटी से निकलते हैं, तो इसकी बहुत जगहों पे एप्लीकेशंस हैं chaos थ्योरी की। हाँ
सर नॉन क्याटिक जो है उसको भी थोड़ा सा एक्सप्लेन कर दें,
हाँ
इसके ऑपोजिट क्या
हाँ
चीज़ है?
नॉन क्योटिक फिर ऐसे होते हैं कि जिनके या फिर वेरिएबल्स बहुत ज़्यादा कम है, या फिर अगर वेरिएबल्स बहुत ज़्यादा भी हैं तो वो वेरिएबल्स आपस में ना रिलेटेड हैं। तो अगर आप उनके दरमियान रिलेशंस कायम कर सकते हैं ना, तो आप उस सिस्टम को रिड्यूस कर सकते हैं। तो अगर आपके पास इतने ज़्यादा रिलेशंस पाए जाते हैं उस सिस्टम के अंदर, तो फिर वो सिस्टम जैसे हम कहते हैं इंटेग्रेबल है वो सिस्टम, उसको हम फिर इंटीग्रेट कर सकते हैं, उसकी हम फार्मूला डिराइव कर सकते हैं उसके लिए कि वो फार्मूला मिल जाएगा, उसको मैं प्रिडिक्ट कर लूँगा कि आगे जाके क्या होगा इसके साथ। तो उनको इंटेग्रेबल सिस्टम्स भी कहते हैं। अगर लीनियर सिस्टम है वो तो लाजमी बात है कि क्योटिक है ही नहीं, अगर लीनियर है उसको तो सॉल्व करना बहुत आसान है। लेकिन अगर नॉन लीनियर भी है लेकिन उसके अंदर कुछ आपके पास इनवेरिएंट्स कहते हैं उन्हें, या फिर इंटेग्रल्स ऑफ मोशन कहते हैं उन्हें, वो प्रेजेंट हैं, तो फिर आप उसको भी फिर आप वो नॉन क्योटिक हो जाएगा। लेकिन अगर आपके पास बहुत ज़्यादा वेरिएबल्स हैं और उनके दरमियान इतने रिलेशंस नहीं है आपके पास, तो वेरिएबल्स बहुत तरह से चेंज हो सकते हैं, डिग्रीज ऑफ फ्रीडम बहुत ज़्यादा हैं, तो फिर वो क्योटिक हो जाता है। लेकिन जिस तरह मैंने शुरू में कहा कि अभी ना यूनिवर्सल डेफिनेशन अभी तक उस पर हम लैंड नहीं हुए कि हम कह सकें कि एग्जैक्टली ये क्योटिक सिस्टम्स हैं, ये नॉन क्योटिक सिस्टम्स हैं। परफेक्ट डेफिनेशन अभी तक हमें नहीं मिली, लेकिन कुछ अच्छी डेफिनेशंस हैं हमारे पास।
कोई ऐसे फिनोमेना हैं नेचर में जिसमें एक पॉइंट पे तो केओस ज़्यादा हो, लेकिन फिर किसी वजह से डिग्री ऑफ केओस जो है वो कम हो जाए? अगर जैसे वेरिएबल्स, नंबर ऑफ वेरिएबल्स रिड्यूस होते हैं, या पता नहीं कोई ऐसा फिनोमेना हो जिसमें डिग्री ऑफ केओस कम हो, और एक जो सिस्टम है वो एक बहुत ज़्यादा क्योटिक सिस्टम से वो कम क्योटिक और नॉन क्योटिक हो जाए, ऐसी वैसी कोई चीज़?
अब सिस्टम इटसेल्फ तो नहीं हो सकता। अब अगर एक पूरे सिस्टम को आप ले रहे हैं तो उसकी ना उस किसी भी सिस्टम के आप फेस स्पेस बना सकते हैं। फेस स्पेस का मतलब है कि जो जो भी वेरिएबल्स उसके अंदर हैं उसमें से मैं एक मैथमेटिकल स्पेस बना सकता हूँ। तो उस मैथमेटिकल स्पेस के किसी भी आप पॉइंट पे हैं ना, तो वो आपको वो एक पॉइंट बता रहा है कि वो पूरा सिस्टम अभी किस हालत में है। तो एक सिस्टम है, उसके बहुत ज़्यादा डिफरेंट स्टेट्स पॉसिबल हैं एक सिस्टम के, फिजिकल सिस्टम के। तो ज़्यादातर जो सिस्टम्स होते हैं ना, उनकी जो पूरी फेस स्पेस होती है, मतलब सेट ऑफ ऑल पॉसिबल स्टेट्स, उसमें हर स्टेट क्योटिक नहीं होती। ऐसे भी बड़े सिस्टम्स होते हैं जिनके कुछ रीजन्स होते हैं जो कि नॉन क्योटिक होते हैं, मिक्स होता है उनके अंदर। कुछ स्टेट्स के अंदर अगर आप हैं उस सिस्टम के तो चीज़ आप प्रेडिक्ट कर सकते हैं, लेकिन और स्टेट्स के अंदर है तो फिर वो आउट ऑफ कंट्रोल हो जाती है चीज़। तो फिर वेदर के केस में भी ऐसा हो सकता है, अगर इतनी हवाएं नहीं चल रही, माइल्ड हवाएं चल रही हैं फॉर एग्जांपल, और टेम्परेचर भी इतनी तेज़ी से चेंज नहीं हो रहा, फिर शायद आप वेदर को काफ़ी आगे तक भी प्रेडिक्ट कर सकें। जिस तरह फॉर एग्जांपल एक बड़ा सिंपल सा वेदर सिस्टम है, फॉर एग्जांपल मार्स है, उस पर तो बहुत ही कम हवा है, या फिर कोई एक मैथमेटिकल सा मॉडल ले लें, आप बहुत ही सिंपल सी आप वेदर का सिस्टम ले लें, उसके अंदर फिर वो नॉन क्योटिक हो जाएगा। तो मतलब कोई क्योटिक कोई सिस्टम है, बात करने का मकसद ये है कि ना कोई भी सिस्टम है अगर वो केओस शो कर रहा है तो ज़रूरी नहीं है कि वो हर हालत में ही केओस शो करेगा। अगर आप उसको ख़ास पैरामीटर्स की वैल्यू पे ले आए, उसको आप सिंपल विंड स्पीड आप लो कर दें, हर चीज़ आप लो कर दें, फिर वो स्टेबल भी हो जाएगा। इस तरह आपने वो वीडियोस आपने देखी होंगी, लेमिनर फ्लो की आपने वीडियोस देखी हैं, लेमिनर और टर्बुलेंट फ्लो की, बड़ी ज़बरदस्त, जिस तरह यूट्यूब पे और इंस्टाग्राम पे नहीं आ रही होती छोटी छोटी वीडियोस, तो उस पर वो बड़ी ज़बरदस्त, वो देखना आप। तो लेमिनर फ्लो होता है कि उसके अंदर ना फ्लूइड की स्पीड इतनी कम होती है और उसकी ज्योमेट्री ऐसी होती है कि ना बग़ैर किसी इंटरफेरेंस के पानी आराम से पाइप से निकल रहा होता है। वरना नॉर्मली जब निकलता है तो उसके अंदर बहुत इंटरफेरेंस होती है ना, कहीं पे कॉन्ट्रैक्ट हो रहा होता है, कहीं ड्रॉपलेट्स बन रहे होते हैं, फैल रहा होता है। तो ख़ास आप ज्योमेट्री उसकी रखें और स्लो स्पीड रखें उसकी ना। पानी के साथ आप ट्राई भी कर सकते हैं, पाइप है, जब उसकी कम स्पीड होती है तो वो बिल्कुल एक स्ट्रीम की तरह आता है, जब स्पीड बढ़ जाती है फिर वो फैलने लगती है, टर्बुलेंट सा हो जाता है। तो ये है तो वही सिस्टम पानी का सिस्टम है, पानी का फ्लो है, लेकिन फॉर सर्टेन वैल्यू ऑफ वेरिएबल्स वो सिस्टम डिटर्मिनिस्टिकली बिहेव कर रहा है, उसको आप आराम से प्रेडिक्ट कर सकते हैं। फ्लो लाइंस उसकी बिल्कुल एक दूसरे के साथ इंटरफेयर नहीं करी। लेकिन अगर आप उसी सिस्टम में वैल्यूज़ बहुत बढ़ा दें, पानी की स्पीड बहुत बढ़ा दें, या फिर पाइप को कॉन्ट्रैक्ट कर लें, कोई भी उसके साथ आप उसको छेड़ें आप उस सिस्टम को, तो उसके अंदर फिर केओस आ जाएगी, टर्बुलेंस आ जाएगी उसके अंदर। तो बिल्कुल ऐसा हो सकता है कि विद इन द सेम सिस्टम यू कैन हैव बोथ केओस एंड वो नॉन chaos. जी.
Thank you. For the same, what Moin Saab is saying, I think one example could be these runners. If we are talking in terms of biology, the 100-meter sprinters, when they are going, some of the very great sprinters, you've seen that they seem very relaxed. At a particular time, their body comes into their control, and the chaos becomes more controllable. And same with those marathon runners, that they learn, and they are not very muscular and so powerful, but they with the time they learn, and they can run up to 50 kilometers. So all the chaos in the body, once they start to control it, it becomes more relaxed, and they find it easy. Some of the sprinters. I would think that can be one of the examples.
Maybe, but maybe it is a bit difficult to convert this into like the mathematical form, because this is a kind of a qualitative example. This is based on the internal feelings of
an
the runner,
individual.
how he feels at the moment. He's feeling relaxed or not, or he's feeling very tightened up or very tired and all over the
They
place.
are normally told to relax their body.
Yes. So we are talking about it. So chaos theory basically wants to study something that we can have equations for.
Yeah.
So for example, if you can set up an equation for a runner based on his body mechanics, and you can somehow, and then you can maybe say something about whether that runner is running chaotically or running in a relaxed manner.
Yeah. Secondly,
Maybe.
just one more thing. The climate change, the factors which are affecting the whole of the climate, but we have to consider the power of nature as well. That if we somehow control these factors which are damaging the climate, if we start controlling them, then the weather can actually reverse and go backwards, and the nature has its power to heal itself and can reverse itself. And sometimes you see naturally something starts to go back to their normal shapes.
But still, there is something called tipping points as well in the climate, which have been discussed a lot. So if you stay beneath those tipping points or below those tipping points, then nature can probably heal itself if we stop doing what we are doing.
Yes.
But scientists have predicted that if you cross certain tipping points, for example, there are many tipping points, there are documentaries on this as well. The ocean reaches a certain temperature, or the forest cover reaches a certain percentage, for example, then new feedback loops will be introduced into the system. For example, if the ocean becomes too hot, then it will not be. So this is a physical fact that as water gets heated up, it loses its ability to store more carbon dioxide. So the ocean is the greatest absorber of carbon dioxide, which is the greenhouse gas. But if you keep emitting greenhouse gases, and the overall temperature keeps increasing, then the ocean temperature will also increase. Ocean will start losing its ability to store more carbon dioxide. And then as you are emitting more carbon dioxide from the factories, the ocean will also start releasing more carbon dioxide that it can no longer hold. And when it starts releasing carbon dioxide, then it will further reduce its ability to store carbon dioxide, and this will start a feedback loop, and more carbon dioxide will be released into the atmosphere, and we will accelerate towards
It's a vicious cycle.
vicious cycle. So there are many tipping points like this, so we should be careful of these tipping points, and nature doesn't always have the ability to reverse itself. That is why scientists are so concerned.
I think this climate change is a very suited sort of an area for chaos theory. So it must be chaos theory might become even in bigger and bigger demand. And I'm just wondering that with climate, modeling, one, you have the physical sort of the various physical parameters, then you have human behavior, and you could have industrial trends. You have so many different systems, and they all there's fusion or there's sort of interaction going on between these different systems. So I think that if this can be modeled,
Exactly.
I think chaos theory has suddenly it might have
Yes.
there might be big demand. So is this happening?
Exactly. So
Is
it has been happening
Yeah.
ever since chaos theory took off. People started applying it to all sorts of different fields. I have only given you a small sampling: chemistry, economics, engineering, traffic, meteorology, physics, astronomy, and everything else, biology. So this has been applied to the stock market and everything which has a high number of variables and lots of interaction, non-linear behavior. You can apply, and you have to apply chaos theory because there is no other way. Otherwise, you can't really study it. Obviously, chaos theory is the only thing you have to study it properly. So, climate is one of the most pressing issues of our time, and chaos theory is probably the only real tool we have. Uh, Coupled with obviously with lots and lots of computation, because without computers, chaos theory, we wouldn't be able to do anything with chaos theory, obviously, because you need lots, and because obviously, as I've told you, it's not possible to derive equations for chaotic systems. If you had a equation, then you would have just put t is equal to 100 years, and then it would have just spit out the answer that this will happen after 100 years. But you don't have equations for these systems. So all you can do is compute it numerically using computers. You need large computers. That's why when chaos theory only emerged properly when computers were invented. So you need the methods of chaos theory and lots of computation to say things about the climate. And people have also obviously already done these sorts of simulations. And using those simulations, they have said what they are saying, the climate scientists, that we are heading towards disaster.
This is the last thing that I want to ask too many questions. But conference of parties, the COP that happens every December, you don't find any mention of chaos theory or any like differences between different approaches of chaos theory. You don't hear it's not even there's no trace of it. So is this all happening really somewhere in the background? And
Yeah, probably
and,
these models have already been incorporated into the models. So there is probably not much need to say chaos. We are using chaos theory over here. But if you dig deep into those models, you will probably find these kinds of things. Yes.
Sir, as you said, if you give more freedom to something, it becomes chaotic. Is there any example in history that where giving more freedom has led to chaos? If that is what we learn from them.
Yes, so as I've told you, there are many examples. So, for example, I told you about the three-body problem. Yes, solved by Poincaré. So before that, Newton had solved the two-body problem, in which only two bodies are orbiting each other, like the Earth and the Sun. So Kepler also solved it, and he told us that the orbits are elliptical, and you can solve it completely using Newton's equations. The next thing was adding complexity. The next step was, if you have three bodies interacting with each other, like the Earth, Sun, and Moon, then can you predict their motion? Newton was not able to solve that problem, and he left it for future generations. But then Poincaré came, and he discovered that there is no closed form solution for the future trajectory of each of those planets. The system is already too complicated, even with three bodies. So that is a good example of adding complexity, adding freedom to the system, leading to chaotic behavior. And there are many others. About the Duffing oscillator, I gave the example of Duffing oscillator. You added the x cube term, and it becomes chaotic. Before that, it's not chaotic. And you can do this with any kind of system. Reduce its number of variables, it will become a predictable system, and increase it, and you will see at a certain point it will become chaotic.
उस्मान सुबहानी है, उनका ये क्वेश्चन है, आर देयर एनी chaotic intergalactic motions within the observable universe?
Yes, there must be, because as I have told you that the solar system also, everything behaves chaotically. There is almost, because everything in the real world is connected with each other. All of us are connected, and all the particles are interacting with each other. Even in space, the bodies are so far apart, and they, relative to their distances, they move so slow that on our time scales we can't see the effects of chaos the way we do with, for example, beaker of water. We can see the chaos there immediately. But for example, if you take the perspective of advanced aliens, for example, who can see millions of years in 1 second, for example, then they will also see the motions of the galaxies and planets behaving like a beaker of water and behaving chaotically. So on the scale of the solar system, the time of instability is about 4 or 5 million years. If you go to galactic scales, then probably this will increase further. I don't know what the exact numbers for galactic instability is. Probably some millions of years, greater than 4 or 5 million years. But everything is chaotic because obviously, as I've told you, when you go to 3 bodies, already you have chaos. And in the actual universe, you have millions and billions of bodies. Even though they are interacting weakly with each other because they're very far apart, but on large enough time scales, everything is chaotic. So it's like the study of non-elephant animals, as the physicists say. Almost everything is chaotic. Just like almost every animal is not an elephant. Right?
Thank you, Shailen.
Thank you.
Zabardast.
Thank you.
Thank you.